Thanks to the organizer and the chairman for giving me the possibility to present my contribution entitled Development of an Innovative Gas Turbine Chemical Looping Combustor for Carbon Negative Power Generation. I am Dr. Pietro Bartocci, and this is the title of my Marie Curie project, which I'm managing as an individual fellow at the Spanish Research Council, CSIC, is in particular at the Instituto de Carboquímica located in Zaragoza. The presentation is structured starting with an introduction to current energy scenarios. Then we will focus on decarbonizing the gas turbine sector and our experience, which was previous respect to the current project, and started when I was collaborating with the University of Perugia and the Becker Hughes industry. The production site is located in Florence. And then I will introduce the GTCLC-NEG project and further development in the project itself. So dealing with the energy scenarios, we see from the statistics of IRENA to the left that the renewable energy is growing steadily. But on the other hand, the statistic of Rystad, which is an ONG based in Norway, with multinational sites also, say that fossil fuel consumption is not going down as expected. So it remains steady, even if we know that it has a very important negative impact on climate. So for this reason, carbon capture and storage could be a solution to avoid that these fossil fuel power plants will be turned into stranded assets. So to continue running these power plants and at the same time reducing their impact. In particular, carbon capture and storage, if applied to the bioenergy sector, can be a carbon negative technology. This means that, as we will see, carbon dioxide can be absorbed from the atmosphere and stored underground. These carbon negative technologies are taken into account also in the IPCC reports. And they are colored here in yellow, and there are different scenarios for their employment, and they could allow to offset some of the carbon emissions which will be anyway present, in the industrial and other sector where they are difficult to be reduced. So how does bioenergy with carbon capture and storage work? Mainly CO2 is absorbed from the atmosphere through the photosynthesis process, which is performed by a biomass, which could be herbaceous or woody biomass. Then this biomass could be transformed in energy directly or previously converted in a biofuel, and then transformed into energy in power plants. We are speaking about thermochemical power plants which combust biomass. The CO2 coming from this combustion, if it is captured and stored underground, it could be a negative technology, carbon negative technology, because we actually absorb the CO2 and we store it underground. So my project, which deals with carbon negative emissions gas turbine, started through a previous collaboration, which was between the University of Perugia and Baker Hughes. And we see here the results of a paper which was published in 2021. So this was a study on a new model of gas turbine developed by Baker Hughes in Florence. And what we did was a detailed analysis of the emissions linked with the raw materials used for the gas turbine production, for example, steel. Here we see in black the emissions which are corresponding to countries which energy mix is particularly polluting. This means that they have a high carbon footprint of their electricity production. And this can happen, for example, in developed countries or developing countries, like China and India. While in the white case, we assume that sufficiently clean technologies are used, for example, a big penetration in the energy mix or electricity mix, at least, of renewable energy, and this kind of more developed energy production technologies. We also evaluated with the same approach, which is mainly based on life cycle impact assessment, and the impact of all the operations which are performed in the production company, and they are necessary to produce the gas turbine. And finally, we arrived at the analysis of the different impacts of the different components of a gas turbine in order to perform design process which could take into account not only the economic parameters, but also environment and social parameters. This action was preliminary to to the project that I am presenting, because life cycle assessment can be a technology which allows us to select the less impactful solutions and approaches. This is followed by fully utilized by the whole oil and gas sector at the moment. And as we know, the most important part related to the impact of a gas turbine is when it combusts fossil fuels. So this is the part where we focus in the next steps of the presentation. So why integrating a chemical looping combustor into gas turbine? Economic and environmental aspects. This is a first study I did on a hypothetical plant. We see here the reduction reactor and the oxidation reactor, which are linked into a loop. This is the chemical looping combustor. Then we see a compressor which provides air to the oxidation reactor, and the air which is used to oxidize is also used to expand in the turbine and provide electricity. To optimize the efficiency of this plant, we see many heat exchangers which are needed to integrate heat among the different parts of the plant. This concept is not new. It has been discussed by the Technical University of Vienna, also by Dr. Wolf and Dr. Jan in a previous paper, and by the Polytechnic University of Milan. Here is an example of the concept plant developed by Dr. Wolf and Dr. Jan. And here is also an example of the plant developed at MIT, which I found interesting to propose here because the conference is hosted at MIT itself. And here we see that the peculiarity of this plant is that it's based on a combustor, which is a rotary combustor. So at the MIT, they designed a very compact version of a chemical looping plant in which the reduction and oxidation can happen in only one reactor. So this was the importance of their approach. Why it is needed, this work and this process and this project? They are needed because even though this process has been already studied and theorized, at least in theory, there are still some barriers which prevent from its application at industrial scale, and so its commercialization. So the first barriers are that we need efficient oxygen carriers, maybe bimetallic oxygen carriers. So we have also to grant low attrition of the oxygen carrier, and the oxygen carrier has not to form dust, because this could be a problem when the dust is not efficiently separated by the cyclone and we find dust in the gas turbine, for example. The kinetics of the chemical looping when applied at high pressure and high temperature is not known well at the moment. And there are few plants, mainly on pilot scale, working with pressurized condition. And this is a brand new field which needs to be addressed and researched. Also, reactor injection can be a problem when we speak of pressurized condition and when we speak especially of solid fuels, for example. The last aspect, which maybe is also very important, is the electrical efficiency of the plant. If we want to do a combined cycle using chemical looping combustors, we will probably lose efficiency, 4 or 5 points of efficiency. So the problem is how to evaluate this if we operate with biomass. If we operate with biomass, we can discuss about the loss of the efficiency, because being a carbon negative technology, we can assume that the more fuel that we combust, the more CO2 we will reduce. So this will be the analysis of the efficiency should consider also other issues like economic issues and the price of carbon credit, for example. So dealing with the carbon capture through chemical looping combustion process, I guess that everyone knows the process. This combustion where oxygen is provided by metal oxide, and so it is not provided by air. The advantage is that in the exhaust gases, we don't have nitrogen, which is contained in air, and we don't have oxygen, because only the needed oxygen is liberated by the metal oxide. So we have two streams of water vapor and CO2, and if we condense the water vapor, we can have a pure stream of CO2 which can be captured at very low costs. We have done a feasibility study which wanted to create an energy scenario for Italy in 2030 and try to see what happens if we substitute the combustor of the combined cycles, which are now burning natural gas in Italy, with a chemical looping combustor. The costs of the chemical looping combustors and everything are taken from literature. Obviously, this is a study which wants to promote this technology, but we have also to consider that the technology should be still optimized before joining the market and have a wide application. So the data about the Italian energy system are taken from the National Energy Strategy and the National Integrated Plan for Energy, and a model which is the Times Italy model, which is a version of the Marshall Times model, which is used from the International Energy Agency to perform energy scenarios. All these data of the different documents on energy planning in Italy have been inserted in the energy plan software developed by Aalborg University in Denmark. And we have recreated the energy scenario for Italy based on the targets which are indicated in the energy strategies for 2030. We see that the contribution of natural gas is still very important, and we assume that the natural gas combined cycle plants which are present in Italy will not be stranded assets. So they will continue to work and repay also their investment. What we want to do is to substitute the combustion chamber with a chemical looping plant, which is the topic of my project, for example. These are the capacities of the combined cycles that we have in Italy, and this is the electricity production. And we see that our final scenario introduces a penetration of renewable energy, which is around 62%. And we see here the benefits in terms of CO2 reduction and the costs of the total system. If we compare the costs of the new system, like on the right, where we introduce chemical looping combustion with the business as usual, which is proposed in the left, we see that there is the investment needed to upgrade the plants is not so huge. The investment and the operating costs also depend on the carbon credits that we have, and the carbon credits that are much higher if we compare to the estimates that we had in 2018, for example. So if the carbon credit will reach a threshold of 130 euro per tons, we can easily say that all the investment and all the costs necessary to run this system could be balanced by the carbon credit and equal the business as usual scenario. So from these premises derives my project, which uses chemical looping combustion not only for CO2 capture, but also for carbon negative technologies. So what we want to do is to use biofuels into this technology. To study how to develop such combustor and develop this technology, I was hosted as a Marie Curie Fellow in the Instituto de Carboquímica in Zaragoza, Spain. by the group of combustion and gasification, which has several research lines, as you can see, and in which they have facilities to prepare oxygen carriers, test them in pilot plants, and then scaling and optimization of the entire combustor. Here are batch plants which can work with gaseous, solid, and liquid fuels, and also continuous plants. We have already discussed the idea of coupling chemical looping with the gas turbine, so I will not speak about it again, while I will introduce the project, which is mainly based on the preparation of oxygen carrier in batch tests, modeling of particle, reactor, and the whole plant, and then continuous pilot test and reactor design and guidelines to help to build our first prototype, for example. These are the results of the modeling part, where they have been already published. It's a model for a batch reactor, and this was done in MFIX software, which was developed by the National Energy Technology Laboratory, which is part of the DOE in the US. And the results of the model are based on kinetic, which has kinetic parameters which have been derived at the institute where I'm working now in Spain, and then the visualization of the results. These are the trends of pressure, velocity, and temperature, then gas velocity and volumetric flow. Also, the products of the reaction are obtained, and the conversion factor of the oxygen carrier, which is the parameter we mainly use to validate our result. An example of a result is provided here. We have a YouTube channel for the project, and this is a batch reactor like the one we use in Spain, working with biomethane. And the interesting part is that if we see around 3 minutes, we see that the reaction path completely changes, and so we are able to establish when the oxygen carrier is exhausted, terminates its efficacy, and so the maximum length on the complete reduction cycle. Same modeling has been done in collaboration with the Huazhong University of Science and Technology. Here we see the batch reactors, which have been validated from pressurized GA data, which have been measured also during our project. And here we see the age of the reactor, and that the fuel, which in this case is syngas, so H2 on the left and CO on the right, decreases because it reacts with the oxygen carrier at different pressures. Here we see the behavior at different temperatures. We see also the length of the cycle, because here we see that the fuel does not react, recovers from full concentration, and this means that we use this data to evaluate the length of the total cycle. Finally, we see the trend of reactivity of hydrogen and carbon monoxide at different pressure. We see that carbon monoxide is much more sensitive to pressure respect to hydrogen. And we see that hydrogen has a slow reactivity at around 15 bars. We see also that the behavior of syngas can be modeled just by adding the behavior of carbon monoxide and hydrogen. Through this data, we have calculated the inventory of the oxygen carrier, and we found a result which was not predicted by the experiments done with the pressurized TGA. With the pressurized TGA, we saw that the reactivity had an opposite trend. This means that with the increase of pressure, the reactivity was decreasing. In this case, we see that the reactivity increases with the pressure, and this means probably that the pressure improves the heat exchange and the mass transfer inside the reactor. And so the reactivity, as you know, has kinetic parameters and heat transfer and mass transfer parameters. So this means that when we test the oxygen carrier in a reactor, the heat transfer and mass transfer can balance or overcome the effect of the kinetics. The same plant, based on the CFD model and on the experimental models, has been developed through Aspen modeling, and we have produced guidelines to develop such carbon negative combustors for gas turbine. The guidelines say that we start with the power of the gas turbine, then we calculate the air mass flow, then we calculate based on a stoichiometric combustion formula the fuel mass flow, and so the oxygen carrier circulation rate, the inventory, and we arrive at the final design of the two reactors, the air reactor and the fuel reactor. This has been done already in Aspen, and we have also made an optimization strategy for the combustor to maximize the efficiency of the plant. To maximize the efficiency of the plant, much of our study was done on the excess air which is used in the air reactor. This can be 1.2 up to 3 times or 3.7 even in some publication. So what we saw in our calculation is that the more the higher is the air excess air to fuel ratio, the higher is the efficiency of the plant. This means this is based on two advantages. The first is that if we have more air, we can control better the temperature in the air reactor. And the second advantage is that if we have more air, we will have more power, because this will expand in the gas turbine, and we will produce more power with less fuel. So the efficiency will be high. How to maximize the air excess air to fuel ratio? We have done two thermal balances of the air reactor and the fuel reactor. These are connected, so in the most of the cases the heat is given from the oxygen carrier, which is transported from the air reactor to the fuel reactor. So if the heat is transported, we can say that the two terms of the two equations are equal, because they establish an equilibrium between the two reactors, which are connected. And so we have only one variable to optimize, and this is the excess air used at the air reactor, according to our study. So in conclusion, we have performed CFD and Aspen studies based on experimental data to obtain guidelines for the design of such carbon negative combustor for gas turbines. Future development are surely based on economic analysis, because this is also to be taken into account. The project has been founded by the Marie Curie framework of the European Union. And we also thank Chalmers University for support and feedback. The contacts, these are my contacts if there are some questions on the project and on the presentation. The project website is the following, and we have a repository where you can consult and download the publications done during this project. Thanks for the attention, and again to the organizers and the chair.